Okay, good evening, everybody. Thank you for coming out to hear about large earthquakes. If you got 10 out of 10 on that little trivia quiz, you probably watched too many bad movies, which is one of the things I do. I actually have taught a class called Earth Science in the Cinema, where we go through a lot of those movies and discuss what's factual and what is more artistic license. So I hope you all have seen San Andreas. Has anybody gone to see San Andreas? A few? Yeah, it's mostly artistic license. You're not going to see too much of that in today's movie, or today's talk, but there are themes like you see right here that are real occurrences of kind of Hollywood-esque devastation. This is from the 2011 earthquake that struck in Japan. And this is one of a sequence of very large earthquakes around the world that I'm going to give you a few highlights about what we're learning about those events, what they involve, and what science we're learning from analysis of them. Let me set the stage. I expect here on the West Coast, most of you are pretty familiar with earthquakes in general. I'm not going to give a very technical or mathematical talk. I want to go over just a few of the basic ideas. We have the fundamental idea, which is that the Earth's surface, the rocks near the surface, they're stiff, they're brittle, but it's as though we had a jigsaw puzzle of broken rock at the Earth's surface, where all the jigsaw pieces are moving around relative to one another. This is the process called plate tectonics, where large chunks of rock, like the Pacific plate, the North American plate, are moving at on the order of 10 centimeters, 5 or 6 inches with respect to each other every year. And where they rub against each other on their margins, plate boundaries, is where we have earthquakes occurring. So earthquakes are not uniformly distributed over the planet. They're concentrated on the edges of these mosaic of big chunks of rock that are the Earth's plates. And we've understood this only for about 50 or so years. There was kind of a revolution in understanding in the 1960s that led to earth scientists coming to appreciate the nature of plate tectonics on the Earth. And this concentration, all these white dots are where earthquakes are. They're near these plate boundaries for the most part. And that will prove true of most of the events that I'll be talking about today. Now, the map here shows the distribution of really big earthquakes. And seismologists use the convention that if we measure the size of an earthquake, we measure it from the strength of ground shaking. And if it's on our measurement scale, it was originally introduced by Richter, but it's been updated since then. If we measure it as a magnitude 8 or greater, we call it a great earthquake. Okay, so that doesn't mean it's great in the good sense. It means great in the really big sense. So if the plot here shows the distribution of great earthquakes around the world since 1900 in either the blue beach ball shapes or in these green dots. And since 1900, you can see that they kind of concentrate on the margins of the Pacific plate, that huge chunk of rock that's moving coherently on the Earth's surface relative to the others, and where it rubs against other plates, like along this region of Mexico or South America, or along Alaska, the Aleutians, near Japan, along Tonga, Solomon Islands over here, or where this plate, the Indian plate, is rubbing against Southeast Asia. That is where the giant earthquakes occur, the magnitude 8 earthquakes that we've recorded in the past 110 years or so. And we go back to 1900 because that's when they first deployed global seismic instruments that could detect the ground shaking from earthquakes and kind of systematically measure how big they were. So these events are kind of on the margins of the Pacific plate, and they're consistent with the basic idea of plate tectonics, that where plates are rubbing against each other is where you build up the deformations that suddenly release in earthquakes. We'll talk a little bit more about that. The green dots are the older ones. Before 2004, these beach balls are displays of the geometry of the fault that we can determine from analyzing recordings of the ground motion in different places on the Earth produced by each earthquake. And if the beach ball is kind of blue or purple in the center, that would indicate that one plate is shoving down under another. And in this case, there's a plate here, the Nazca plate, which is being overridden by South America, which is moving westward. And these indicate that those two plates are converging. If you have this type of four-lobe pattern beach ball, that indicates that you have horizontal shearing between the two plates. That involves plate motion between the Australian and Pacific plate. Or out here, these are breaks within the Indian plate. And if you have white in the middle, that indicates regions where the plate is pulling apart, being extended. And we have a couple of examples of such events shown here. And those beach balls, if you count them up, there are 18 of them. And they are the events that occurred between 2004 and 2014. So there's 18 events in 10 years. This is the only mathematics you have to remember. That's divide that number of events by number of years. You got 1.8 per year. It's a big number. It scares my cat. Because if you look at the last 100 years before that, the average was less than 1 a year. It was 0.7 per year. So during that 10-year period, from 2004 to 2014, there was a 250% or a 2.5 times increase in the rate of giant earthquakes around the world, measured as magnitude 8 and larger events. So that sounds kind of ominous, and maybe Hollywood could make a story out of a global earthquake cascade or catastrophe. I don't think that's what's going on. Some of these events are interacting. Events in close proximity, the sequence here is going to begin with the 2004 Sumatra earthquake. It did change the stress in the surrounding rocks and activate adjacent faulting. So these events are clearly interacting. There are pairs of events like these two events off the Kurils that happened in close proximity a few months apart. I'll show an example of this. So there are clear cases in which these events do interact with one another, but the collection of them is probably not causally linked in the sense of triggering one another interacting on a global scale. Instead, it's more a statistical occurrence that has concentrated the number of events that we've seen in this decade. Now, how can I display that? Here's a plot as a function of time going back to 1900 when we first began to measure the magnitude of earthquakes systematically and robustly, measuring the peak magnitude for 7.5 and larger events, ignoring all the smaller events, which can be destructive, but for the moment we're just cutting them off. So we're looking only at 7.5s and bigger, and plotting each one of these as an individual event with a corresponding magnitude. And you can see how magnitude of events occurs as a function of time with this plot. What you can detect over here is all of these events that have happened in this last 10 years. You count above this level, which is magnitude 8, there are 18 dots here. And those are the events of this recent surge of large earthquakes. And if you go back through time, you see, well, that is unusual. On average, over this whole period, they're only 0.7 per year, less than 1 a year. But there was a time in the 1940s and 1950s where you had a lot of great earthquakes clustered in time as well. And some of these were in close proximity. There were several events along the Aleutians in Alaska, but others were far apart, like the Chile event, the biggest earthquake that was ever recorded, 9.5, was very isolated from the other events. So they were clearly also not interacting together in a collective sense on a global basis, but there was a surge here. And back here, there just weren't kind of comparable numbers of them. And perhaps most impressive is that from 1965 up until 2004, there was a long interval, 40 years without an earthquake greater than 8.5. And I call that the quiet days. That actually had a profound impact on my own research career because, as indicated here, I began graduate school in 1978 in Pasadena at Caltech. And when I got there to work on earthquakes, I didn't know anything about earthquakes, but I thought they'd be interesting. I began working with Hiro Kanamori, who's probably the preeminent seismologist in the world for the study of great earthquakes. And he and I started working on some of the earthquakes that had happened in the previous decade or so. It was very painstaking to collect the data and analyze them. It took us about 6 months to analyze an individual event. And I was very excited. I thought it would be great. I have all these tools. I've learned how to do this. And the earthquakes just stopped. They just ended. So I went on to work on the lower mantle and the core for my thesis, and I didn't work on big earthquakes very much anymore. It was the quiet days. But 2004 came along, giant earthquake in Sumatra, and then just about every 5 months after that, there was a magnitude 8 earthquake somewhere in the world. And it became a great time to study big earthquakes again. So I went back to my old professor, and I woke him up, and I said, Hiro, let's work on these big earthquakes. So we've been working on them for the past decade. And it's been very exciting because during the quiet days, geophysicists did something unusual. They actually invested in instrumentation that would be capable of recording great earthquakes when none were happening. And we deployed instruments all around the world in global broadband seismic networks using new technology that would be capable of recording on scale the shaking from a giant earthquake, unlike any instrument that we'd had before. So all of these earlier events that were the very biggest ones, the ones larger than 8.5, we had 1 or 2 or maybe 0 recordings of those giant earthquakes on scale because the instruments weren't capable of recording them. But we had developed new instruments that would be, and those were deployed globally, beginning about the mid-1980s. And by 2000, we had a very good network of them. So they were in place for the 2004 Sumatra earthquake when it occurred. The geodesists began to exploit high-resolution GPS capabilities. Now, GPS is the location capability that you all have in your smartphone that can tell you exactly where you are within a few meters. A high-quality instrument can tell exactly where you are within a millimeter on a day-by-day basis. And we can put these out and record the position of the plates as they're moving. And you can actually see the plates in motion because they're moving 10 centimeters per year. So it's enough to actually measure the deformation of the plates. And when they suddenly slide and slip, you can sense the motion of the earthquake very clearly with the GPS. And we began to put out networks of these in earthquake-prone areas. Beginning around 2002, they began to have these continuously recording so that we could get high-resolution records of the earthquakes when they happen. And similarly, there was a deployment of instruments after 2004 to record deep-water tsunami waves because of the devastating 2004 Sumatra earthquake. A lot more instruments were put out. And all of these 3 types of technology, seismic, GPS, and ocean pressure sensors that detect the sea wave out in the deep water, became available, produced data for these recent great earthquakes. So Hiro and I were able to use data that we had never had before to study these events. Okay, most of the earthquakes that I'll talk about are occurring in subduction zones. You've got one just offshore of Oregon. It happens to rupture every 300 years in the southern part of this, every 500 years over the entire Cascade margin, if you trust the geologic records. And that involves a plate, one of the lithospheric plates, coming and under-thrusting the coastline. So this could be Portland here. This is done for the Indian plate going down under Sumatra. And these plates are converging. And where they're sliding past each other, they can stick and slip and go through episodic events of building up deformation in the rock and then sliding in order to keep up with the plate motions. The plate motions are going at a few centimeters per year at a very stable, steady rate, but they stick on the margins by friction, and they'll build up deformation here that will release in earthquakes. And that's what's going to cause most of the earthquakes that we talked about here. Now, when the fault is stuck, we call it locked. Friction is sticking it. The thrusting motion of this plate coming in and sinking under this one drives the upper plate backward. It drives it in the same direction in which the sinking plate is going. So you would actually be pulling this plate to the right, and it can flex it and bend it upward. And we can see that motion with GPS before the earthquake. You'll see the coastline is going in the landward direction, the direction that the incoming plate is pushing it, and it's being uplifted. And then when you suddenly slide the fault and you release that accumulated deformation, this will spring forward. If it springs forwards under the ocean, it pushes up water, and this will cause tsunami, and it causes the land to go down above the area that has slipped. So we can see that motion before, during, and after with GPS and observe the seismic waves that are released as the fault is sliding. And it ruptures at this incredibly fast, few kilometers per second rate that probably not too many of you answered correctly. That seems counterintuitive, but think of it as like a crack going through glass. And when you fracture a window pane with a ball and it breaks, your eye cannot see the crack expand through the glass. Same type of high-speed ruptures occur in subduction zones. Okay, so we have 110 years of history of earthquakes, and in some places, like off of Cascadia, we've been able to go back and use geologic records to extend that back even a couple of thousand years and see many repeated earthquakes. On the basis of what we know about each region, you can anticipate how often it has a big earthquake in the past and how long it's been since the last big one. People could use that to anticipate what areas are most prone to have a big earthquake in the near future. That type of work was done going back into the 1970s, early 1980s. People analyzed the history of earthquakes and could identify zones that were either red, which meant that they were capable of having a big earthquake, and it had been a long time since the last one, so it should have built up enough strain in the rock that it would be approaching its limiting strength and could have an earthquake. Those were colored red. Areas that had just had a big earthquake recently and released that strain were not thought to have another one. Those were green. So you had a kind of continuum of danger level of future earthquakes. And in 1979, the areas that were colored red, you can see them around the margins, there are a lot of areas. Many of those coincide with big stars, which are where earthquakes struck in the last 10-year period from 2004 to 2014. So in a general sense, 11 out of the 18 earthquakes happened in what we identified as seismic gaps, which were regions that had had prior big earthquakes. It had been a long time since the last big one, and we could expect there would be a future big one. It was not precise as to the time. It was just recognizing that these areas were potentially going to host future large earthquakes. And along Chile, northern Chile, Peru, the Kurils, Japan, Tonga, Solomon Islands, New Hebrides, Sumatra, those were accurately anticipated to be areas where big earthquakes happen, and they did happen, but in the surge in the last 10 years, many of them kind of went in rapid succession. So we knew a bit about where the earthquakes were going to be. Let me start with Sumatra. So 2004 earthquake began this 10-year surge, and it ruptured a prodigiously long rupture. It's the longest rupture we've seen. It goes about 1,300 kilometers along the coast from offshore of northern Sumatra here. Here's Banda Aceh would be right here. It's going to rupture all the way up the coast. Now, it was a surprise to us that it could go so far to the north. It re-ruptured areas that had failed in pretty recent magnitude 8 size earthquakes, but it busted right through them again. And it was in an area where the plate motion is actually almost parallel with the boundary here. So it was surprising that there was as much convergence had accumulated, strain had accumulated for convergence here, but indeed it ruptured all the way through. This event was unexpectedly long, and it was the first of the surprises. And almost every one of the 18 earthquakes that happened subsequently has some surprising attribute that has been revealed by all the seismic and GPS and tsunami data that we have for the first time, probing into the details of each earthquake, and surprise after surprise has been found. So it began with this long event, but that event just produced an aftershock, a measly 8.6 aftershock, that ruptured just to the southeast. So the December 26, 2004 event ruptured here, and in March of 2005, an adjacent region ruptured in an 8.6 earthquake. That type of along the fault extension or sequence of failure had been observed in the 1940s and 50s along the Aleutians and Alaska area. So we kind of expect this type of progression. And then there was an event that ruptured down a little bit to the southeast in 2007. So we have event 1, event 2, event 3, all of these being 8.5 or larger. Now, that's the biggest event of that size since 1965. And 3 of them happened in rapid sequence along here. They skipped an area. They left an area in between 2005 and 2007 that is called the Mentawai seismic gap. It's an area that last ruptured in 1797. It's been surrounded by big earthquakes on either side, and we think that this is an area of high potential for future great earthquake occurrence. So of concern because the city of Padang is right here, has 1 million people living on an island with like just a bridge or two to the mainland, very exposed to tsunami hazard. So there's a lot of interest in studying this Mentawai gap right here. There are also large earthquakes along the region between 1994, 2006, 2010 at very shallow depth that produced even bigger tsunamis than the 2005 and 2007 events, a special class called tsunami earthquakes. I could talk to you separately about those if you're interested. Now, as I said, we began to put out very good quality seismic instruments in the 1990s and 1980s and had a lot of these out in time for the 2004 earthquake. And this is what they look like. They're really boring, right? If you take the lid off, there's a lot of electronics. And these are a special class of instrument that all seismometers have a pendulum in them. But in this case, the pendulum is not allowed to move. And you measure how much electrical resistance has to be applied to keep it from the pendulum from moving. It's a force feedback pendulum. And that's how we measure the ground motions. And we had begun to put these out over the globe. Now, we means IRIS, which is the Incorporated Research Institutions for Seismology. They're the sponsors of this talk. That's a consortium of 110 or so university programs in the US that have PhD programs in seismology. And IRIS kind of gathered together all of the seismological programs and put together this deployment of global instrumentation to provide a research tool for all of the research institutions in the US. But we also make the data openly available to the entire world in real time as soon as it's available. So it's become critical to the national monitoring efforts in many countries around the world, including the US. These instruments are deployed and they're smaller scale but very important efforts from other countries, Australia, Canada, France, Germany, Italy, Japan, and additional countries have been deploying national networks that augment this global set of stations that are operating 24 hours a day, 7 days a week, and providing their signals by telemetry in real time to data analysis centers, such as we have in the USGS in Golden, that operates the National Earthquake Information Center, or the Analysis Center for IRIS, which is located in Seattle. With all those stations operating by 2004, we were able to record ground shaking around the world. And this is going from where the earthquake occurred to the opposite point, which is near the Galapagos. And it's just a display of the ground shaking observed at each station, at each position, as the waves spread away from Sumatra, expanding past all this global network of stations. And this is the first time we ever had recordings of a magnitude 9.2 earthquake on scale ever. And to have suddenly hundreds of them was transformative to the science that we could do to study the earthquake. So we could take these signals and analyze them. These are Rayleigh waves passing along the surface of the Earth sequentially multiple times around the planet. Don't have to worry about the technical details. It's just the shaking of the planet produced by the huge energy release of the Sumatra earthquake with all those equivalent Hiroshima bombs, 5,000. Now we can take the recordings, and seismologists have gotten very good at working on the computer, predicting what the ground shaking should be. This applies F equals MA to a computer program to calculate for a model of the Earth's structure what would be the shaking from a given earthquake. We can do that for the Sumatra earthquake, and this compares observed in black and computer synthetic in red, the ground motions observed around the world. And what these allow us to do is to solve for the distribution of slip and the faulting geometry, as we'll see. In addition to the seismic data, by the time of 2004, we were getting GPS stations from around the world, and particularly around Sumatra, because they're most sensitive and close to the earthquake. And GPS is a fancy antenna. It's a little bit more fancy than the antenna in your iPhone. But we can put out these high-quality instruments that record the precise position of this point on the Earth relative to a constellation of satellites that are in the GPS network, and measure that position either every minute or every day. Nowadays, we're doing it every second to calculate the position here relative to all these satellite positions and keep track of the motion of the plate as a result. Before and after, you can see a change in position from the earthquake occurrence, and these vectors show how the ground moved. So these are all from GPS sites, and they show the GPS station here moved there, and these are measured in meters. So this is about a 10 or 15 meter offsets, and these are as much as 20 meters. Farther away, you have smaller motions. So the motions are concentrated near the region that failed, which was from right around here up to this part of the coastline, and that's where you have these very strong motions. So that gives us GPS data, just like we have seismic data, both of which are telling us how the ground changed its position or vibrated as a result of the energy released from the big earthquake. Analyzing that information, we can come up with models like this. And I'll show several plots like this. So let me just explain what it is. It's along the fault, here is Banda Aceh. So for the 2004 event, it's going to start here, and it's spread all the way up this long, long fault. And it took about 450 seconds to reach it. Even going as fast as it was, several thousand kilometers per hour, it took 450 seconds to get this long distance. And what is shown here is contour, or by color, of how much the fault slipped. Yellowish and red colors are 10 to 15 meters. So 10 to 15 meters of slip here, and on average in these green zones, it's around 10 meters. So over that entire 1,300 kilometer length of fault, the analysis of seismic and GPS shows us that the ground slipped about 10 meters or 30 feet. And it's doing that with a very rapid expansion of the rupture, but the sliding goes at about 1 meter per second. Your eye could actually see the fault sliding. It just wouldn't be able to see the rupture go by. It would go by so fast. So Hollywood gets that sort of right in some of their movies. You can actually see the ground sliding in the San Andreas movie, but they often depict the rupture propagating much, much slower than it does in reality. When it slides, because this earthquake was rupturing out under the ocean, I'm going to show you how it moves the ocean bottom during the rupture, this little animation. Red will indicate where the ocean bottom is lifting up, and it was taking 450 seconds to reach there, so I've sped up. Blue is where the ocean surface, or the ocean bottom is pulling down. So you end up with this big ridge of pushed up rock out under the ocean. Now the rock is stiff, so it sort of stays that way. It's moved up a couple of meters, but it doesn't flow away. It just stays with that deformation. And that is the springing forward of the plate that I showed in that cartoon before. As the fault has occurred, it has sprung forward at the leading edge of the plate contact. Now this is under ocean. So if we now superimpose water on top, what will happen to the water is when it's pushed up, you immediately, very rapidly get a ridge of water, but the water is not stiff, so gravity pulls it away, and you start to have an expanding wave spreading out, controlled by gravity. So this is the generation of the tsunami by seafloor deformation, producing a pulling up or pushing up or pulling down of the ocean bottom that excites the deformation of the water that then spreads out. And you see the waves are going out and spreading over Banda Aceh and to the east, and we'll see other examples. Now, of course, that was devastating. This is a peninsula off of Banda Aceh before and after the earthquake. The tsunami completely overtopped much of the town because it was very low elevation. There was really no high land to escape to, and people were overwhelmed by the expanding, or the incoming tsunami. Now, a tsunami is going to be generated along this 1,300 kilometer long fault. And this shows the red area that's been pushed up, the blue area that's pulled down. This is the expanding tsunami wave, and we'll see it as it spreads out for a couple of hours. And it took 2 hours to reach Sri Lanka and the coast here. It also took 2 hours to reach Phuket in Thailand, because it travels much more slowly in the shallow water here than in the deep water. And so this tsunami greatly expands the area that is affected by the earthquake. You saw the strong deformations in the GPS were very local to the islands. The Nicobar and Andaman Islands had many meters of offset, but the tsunami expanded the devastating impact to all of these surrounding areas on the margins of the Bay of Bengal. And you ended up with 225,000 people dying, the vast majority of which died here, but there were tens of thousands of people that died in Thailand and along Sri Lanka and the Indian coast. And we had 2 hours to warn them, but at the time, there was no operational tsunami warning system in the Indian Ocean. There was an operational tsunami warning system in the Pacific Ocean, operated by the U.S., or by NOAA, but at the time, only one deep water buoy was actually operational for NOAA. So out of 5 that they had deployed. And this caused us to invest in improving the instrumentation of the Pacific as well, seeing the devastation from that earthquake. Now the area that slipped, if you take that length of fault that slipped in Sumatra and you superimpose it on California, it's pretty much the length of California. If you flip it over and put it along the Oregon and Washington coast, it corresponds to about the size of the rupture zone in the 1700 earthquake off of Cascadia. So comparable length of fault, probably comparable 10 to 15 meters of slip, occurred in 1700 off Cascadia, and this is why we're worried about that occurring again in the future, because the coast is exposed. So 2004 was the beginning. I got involved in that earthquake. I was the chair of the board for IRIS at the time. And there was no kind of coordination out of Indonesia to study the earthquake. So I organized an international study of that earthquake to try and quantify what had happened so that we could better prepare ourselves for future big earthquakes. That involved both improving the rapid analysis of the seismic data and the GPS data. It took 3 months to get a good seismic model for the Sumatra earthquake. It took a year to get a good GPS model. And we realized that is just way too long. So the community organized their analysis procedures so they could do it much faster for future big earthquakes. And then they began to come. As soon as we got organized, earthquakes started popping off. The next great earthquakes occurred in the region of the Kuril Islands. Japan is down here, Kamchatka is up here, the Pacific plate is under thrusting this region, the Sea of Okhotsk, and Russia mainland would be over here. And in November of 2006, there was a great under thrusting earthquake, an 8.4. Now at this time, we had improved our algorithms to study earthquakes in real time. We had more international coordination on the data exchange, and there were a few GPS stations, but mainly seismic data for this region. And this earthquake was studied robustly by many people in the community within about a day of the event. So much better than the 3 months for the 2004 earthquake. And it was a surprising earthquake. As I said, every earthquake had a surprise. This one happened in a region where we'd not seen prior great earthquake occurrence. In that map of potential that I showed before, it was an uncertain region because there hadn't been an earlier great event, but we knew that it had been a long time without having one. And indeed, this ruptured, and this shows very strong slip. Up to 15 meters of slip occurred on the shallow part of what's the dipping boundary between the Pacific plate and this upper Kuril Island arc. Most surprising, though, was right after this earthquake occurred, it started popping off little earthquakes out inside the Pacific plate. That's very common. We see that happen for many events when one plate surges forward as it under thrusts and it moves during a large earthquake. It can activate little earthquakes out within the plate that is being under thrust. That happened here, but after 2 months, it led to a second giant earthquake, which now broke within the Pacific plate. So this first one has the typical under-thrusting mechanism. This is the filled-in part of the beach ball here. It tells you the plates are converging. But this one, it's white in the middle, which tells you the plate is being pulled apart. And so you had a coupled effect of an under-thrusting event producing a pull in the plate that fractured the plate. It actually broke it. And the cross-section here shows that. You had this is a vertical cross-section. This is the dipping plate boundary. The Pacific plate's coming in from the right. It suddenly slides forward about 5 meters in an 8.4 earthquake. And just like pulling on a taffy too fast, it caused it to snap. And it broke. It took 2 months for it to happen, but it broke in a second earthquake, which was now a pull-apart type of earthquake. We'd never seen this before. A pair of thrusting and extending faults side by side, clearly interacting. Clearly the change in the deformation from one event was affecting the second event. And this showed us that you can have not just one giant earthquake, but a second one is possible soon after, and we have to be aware of that possibility. The next giant earthquake was in the Solomon Islands. This was an area that I had actually worked on in my very first paper with Hiro Kanamori. We'd studied earthquakes up in this area that had the curious tendency that big earthquakes happen in pairs, lots of doublets there. And when we studied it, this region of the fault, we said, well, there will never be a big earthquake there because we've never seen one, but also because it's a region where there's a boundary between two plates, the Solomon Sea Plate and the Australia Plate, which are both going down under the Pacific Plate. And these two plates are broken, they're not connected, and they have volcanoes and very, very young ocean floor here. And we thought, well, it'll be too weak to ever build up to have a large earthquake. And that was true for about 27 years, but of course, an earthquake happened right where we thought it wouldn't happen. We were surprised. It started right here. It slipped with a big patch of slip, about 8 meters of sliding, and it ruptured right across this join between the Australia Plate and the Solomon Plate. In geology, we call this a triple junction between 1, 2, 3 plates coming together at a single point. And we had anticipated it would be too weak. They couldn't have enough friction build up deformation in this region, and yet an 8.1 earthquake struck right there. And when it slipped, the sliding on this side was consistent with the direction of the Australian Plate relative to the Pacific Plate. The sliding on this side was consistent with the Solomon Sea Plate relative to the Pacific Plate. So we could see in a single event 2 plates going down in different directions, all rupturing within a 2-minute period. And it's told us the seismology is getting pretty good. Later in 2007, there was an earthquake near Peru. This was right up here. It was near Pisco. And we studied this earthquake, and at first it seemed like a very straightforward under-thrusting earthquake. Expect that this plate here is going down at about 8 centimeters per year. It had been a long time since an earthquake happened there. But when we analyzed the earthquake, we found something strange, which was the earthquake started, and then it stopped, and it waited for a minute, and it went again. This was very unusual. We'd not observed this type of behavior. It began with an initial 7.8 earthquake, and that's the area that slipped in red. Okay, and then it's just hung out for a minute, and it kept going. It started rupturing down here, and it expanded in a larger subsequent earthquake that became a magnitude 8 event. This is a real problem for earthquake early warning methods, where if you look at the very beginning of the earthquake, you can measure how big it is, and you think it's over, but then if it waits for a minute and a bigger event happens, you're probably not going to trust your early warning system that a larger event is occurring. Expect that might be later waves from the first event. So this is a real problem, but it happened in this 2007 event. So we went back and looked at 2001, a larger event, magnitude 8.4, that had ruptured along southern Peru, and it had the same behavior. It began with a very modest 7.5 earthquake, ruptured the red area, and as the waves spread out, they went down along the arc, they shook the ground, and they started another earthquake, and they initiated a rupture here that spread back in the direction from the first event. So it looked as though the fault had slipped and the rupture had gone backward and forward. In fact, it had just failed here, and then it started an earthquake over here. It triggered it. Now, all big earthquakes are a cascade, triggering bigger and bigger subsequent earthquakes. Here were nice temporal, spatial gaps between the events where we could actually see this process occurring. And it does present major problems for early warning, because this, you would have said, is only a 7.5 event, and you would have not been prepared for the 8.4 that would happen 30 seconds later. Okay. Another surprising event then happened. This one really caused us trouble for several months. This is at the northern end of Tonga. So this is the Tonga subduction zone goes way to the south where you'd find New Zealand way down there. These are the islands of Samoa. And at the northern end of Tonga Trench, it curves around, and the Pacific Plate is going off to the left. It'll go all the way over to the Marianas. But here, the plate is under-thrusting, under this region, under the Tonga block. It's going down, it's subducting under it. So the plate is actually tearing. This big, thick chunk of stiff rock is ripping. And it's ripping right here, so this plate can go through. It goes through straight over here, and it goes down under the Tonga arc here. Well, there was a big earthquake in September 2009 that we studied, and it was like the outer rise event and the Kurils event. You see it has a focal mechanism with white in the middle. It means it's pulling apart, it's bending or flexing. And this is due to the tearing process, the deformation that's occurring in the Pacific Plate as it negotiates this 90-degree curve in the subduction zone. When we analyzed it, though, we analyzed it with different long-period seismic waves. we got different solutions. These are both solutions for the same event, but they don't look the same. That's very unusual. These are using two different methods from seismology that almost always give us identical solution, a very similar solution. But here they were significantly different. And this told us that something strange had happened during this earthquake, because we're used to these being consistent. Well, after a couple of months, we deduced that this earthquake, which was tearing or breaking within the Pacific plate, had actually activated thrust faulting on the boundary between the Pacific and Tonga blocks. So did just the opposite of what had happened in the Kuril Islands, where you had had a situation of in the Kuril's initial thrusting causing breaking of the plate. In Samoa, we had breaking of the plate producing thrusting. So it was similar type of interaction, but reversed in the sense. And we had never observed this before. We're only able to deduce this by having a combination of really good seismic data that we can analyze, and there was one single GPS data on the island that went the wrong direction to be consistent with this normal faulting. And we were able to deduce that this was an 8.1 extending fault, breaking the plate as it bends to go down, but it produced a magnitude 8 thrusting on the Tonga interface. And that's actually the biggest thrusting earthquake we've seen in Tonga in the 115-year history. Okay, that brings us to just a couple more events I'm going to talk about. 2011. Situation here is the Pacific plate coming in from the right, 9 centimeters per year. It's under thrusting under Japan. Now in Japan, in 1995, they had a very devastating earthquake down to the south in Kobe. After 1995, the Japanese government invested a tremendous amount of money, $1 billion, in seismic instrumentation and GPS instrumentation to improve their preparation for the next earthquake. It really paid off in this event. What is shown here is the position of GPS stations that they had put all over the mainland. There's about 1,200 of these high-resolution GPS stations, and they're operating them continuously, and they record as a function of time how much the ground is moving. And before the earthquake, it's a little bit hard to see, these vectors all are pointing to the left. And they show that along the coast of Hokkaido and along the coast of Honshu, before 2011, the eastern side of Honshu was moving to the west. You go over to the western side of Honshu, it's not moving much at all. So there's a strong variation across Hokkaido. And this could tell us that the plate boundary out here was locked. And they deduced where it was locked. These kind of blue patches indicate zones where the plate was stuck together. And as the Pacific plate's coming in from the right, it's dragging the eastern side of Honshu westward. It's stuck and loaded up. So with GPS, we can see before the earthquake the deformation that's happening and identify the areas where there's strong strain accumulating offshore. But GPS onshore cannot tell you what's happening all the way out to the trench, which is another 100 kilometers away from these patches. It's just blank in their model. It's not because there's no strain there, but they could not resolve it. Well, what happened now is this is the network of GPS sites. This is going to show horizontal motions of each one. These are going to be vertical motions when the earthquake occurs. Not much is happening. This is before the earthquake. These are horizontal motions are negligible. Vertical, these are just bouncing around a little bit due to atmosphere. The earthquake has happened, and what you're seeing is the arrival of seismic waves reaching the stations and starting to move them, and this is how much they're displacing, vertically, horizontally. And the area that's affected is expanding with time as the seismic waves spread out further and further. So you're having the coast, which have been drawing to the west, is now surged to the right. The peak vectors are about 4.5 meters. 30 minutes later, there's another earthquake down here, a 7.9, an aftershock that's going to cause a lot of deformation down in the southern part of Chiba province and just east of Tokyo. So that's a dynamic capture that we had never had before. We had 1,200 GPS stations right next to a giant magnitude 9 earthquake. And you could see the deformation expand through the ground, not just shaking like a seismic record, which will return to its initial position, but with the offset that is captured by the permanent deformation in GPS. And that's what this final plot shows is the deformation that occurred as the eastern side of Honshu surged to the right 4 or 5 meters. And you can see that on the western side of Honshu, it didn't move that much. It hadn't been flexed that much. So you're seeing the buildup of deformation and release. And this is the earthquake cycle that allows us to anticipate the behavior of earthquakes. Now, the seismic waves spread through the world. And on that day, we were able to get a solution for the faulting. Remember, it had taken us 3 months to do it for Sumatra. We were able to get a solution for the faulting within about 3 hours for this giant earthquake, because we have on-scale recordings from the IRIS Global Seismic Network, could analyze them, and they gave us this model. This is along the boundary where the Pacific plate is under thrusting Honshu. It's a dipping surface, and on that surface we contour up the amount of slip, and this red area here is slipping up to the 60 meters. One of the trivia questions showed that it's the kind of record-setting amount of slip in any earthquake fault that we have observed. It was deduced from seismic waves in this plot. So that was our solution from the first day of the event. If you take this deformation from the seismic model and predict the GPS, you do quite well. And that on the right is just a prediction of the GPS motion that should have been observed. Now the GPS records themselves, they look kind of funny. This is the direction of eastward motion, north, and vertical motion. You look at one of these, initially there's no motion, then it surges, and it comes to a step. There's a step offset of about 1 meter, 2.4 meters in this case. All of this is seismic waves arriving, and then you go to the permanent static deformation. Now we can model the GPS just like we would a seismic vibration, and that's what's done here, is you're actually seeing comparisons of observed GPS in red and synthetics in blue, and they often fit so well that you can only see a single trace. There's a few minor discrepancies. So we have a whole new tool to analyze the earthquake faulting, which is the GPS recordings, and it captures not just the transient seismic waves that are causing the time varying behavior, but also the permanent static deformation from the total faulting. So many people began to study this earthquake. It has a phenomenal data set, seismic data. This is a seismic model. This is a model from just inverting the GPS that I showed. And these are other models of different research groups, largely seismic models shown here. They consistently infer 50 to 60 meters of slip in the shallow part of the trench. Now remember, the coupling prediction from the GPS before the event hadn't shown much locking out near the trench, but that was because it couldn't see that far away from the mainland. And that's where the biggest slip actually occurred. The fact that there was huge slip far offshore out near the trench means that's what produced very strong tsunami, because it pushed up the seafloor out near the outer region. So the GPS locking, it anticipated all the slip would be down here, but instead it extended 200 kilometers out from the coast all the way to the trench. Now, technically then, we have a lot of new data from these different types of data, the GPS, the seismic, and the tsunami, all of which can tell us different aspects of the earthquake rupture. If we analyze just the GPS, we might get a slip model that looks like this. And don't worry about the details, the trenches at the top of these plots. And you get a couple of patches. If you just analyze the body waves of seismology, you get a single patch near the trench. If you analyze surface waves from seismology, it's a little bit more concentrated. But if you put them all together, which is the type of research that we're doing now in my research group and in most of the leading research groups around the world, put together all the different types of data set and simultaneously analyze them, you get a combined model, which is better than any one type of data set will recover. And that's still, this is from seismic and GPS inversion, still has very large slip out near the trench, and it produces very good fit to all the GPS and all the seismic data simultaneously. And that's really the research frontier, is to put all the different measurements together and analyze what happened. And that includes the tsunami data. Now, the tsunami observations have gotten good in the last 8 years as well, or 10 years as well. This is the tsunami sweeping into the coastline of Honshu and overtopping the coastal defenses, most of which were built for a 3 to 5 meter high tsunami protection, but the tsunami came in at about 15 meters high. Now, after that 1995 Kobe earthquake, the Japanese invested not just in GPS and seismic instrumentation, but in tsunami sensors offshore. And these proved very valuable. They're located where these little white dots are. These are all instruments sitting on the seafloor that can measure the water pressure. So they're sitting out on the seafloor, and they've got the ability to measure with little flotation units how much pressure of the overlying water there is. And if the water has got normal kind of tidal fluctuations and it's got wave fluctuations, those are all fairly short wavelength. But if you have a tsunami, it's a very long wavelength, prolonged increase or decrease in water above the ocean floor, and that pressure change can be monitored. That's connected up to a buoy that can transmit the information and can locate or transmit the information to sensors. And this can be retrieved and gives us a recording of the passage of tsunamis. And this is the distribution of NOAA sensors now. Not all of these were operational in 2004, but many were. And we're able to get these deep water recordings of the tsunami waves that we can process and treat just as we can seismic waves and GPS waves. I'll show an example of that. This is how the earthquake started. This is at 30 seconds, 1.5 minutes, 2.5 minutes. This is the area that was slipping on the fault. So the darker red has got 50 to 60 meters of slip. And this is kind of the final configuration of slip. It pushed up the ocean bottom by the amounts here. You can see there's a very concentrated amount of uplift offshore. This is the permanent uplift at 2.5 minutes. And this is the deformation of the seawater surface above it. And that's going to spread out as a gravity wave. So what you're going to see here is the earthquake happens fast. The deformation is in 2.5 minutes. It's going to take 30 minutes for the wave to get to the coastline. So you get this initial bulge very quickly. And that's the pushing up of the water out, where you get 60 meters of slip at the ocean floor, about 4 or 5 meters of which was uplift. This wave is coming in on the incident on the coastline. Now this is Hollywood artistic license. It's not really that big. Japan is not that flat. This wave in the deep water is several meters high. But you can see it's a very long, broad wave, so it's a huge amount of water that's coming in. And it's going to pile up as it comes onto the shore and get bigger, and then it's going to sweep up onto the coast. The peak run-up is around 40 meters, or 120 feet. The average height of the tsunami along the Sendai Plain is 15 meters. The height at the Fukushima nuclear power plant was 15 meters. So this wave, you can see it's piling up, and it's going quite slowly. As it's coming to the land, it passes over all those ocean bottom pressure sensors that record the signal. You still have about 15 minutes before the wave gets to the land, that if you had been continuously monitoring those, you would have seen that the wave was going to be much bigger than the Japanese had anticipated. They gave an initial warning of 3 to 6 meters. They've been able to monitor all of the offshore tsunami recordings in real time. They would have seen that it was going to be bigger. And it will splash around on the coast. These are just some snapshots at 10 minutes. 20 minutes it's hitting these buoys. After about 30 minutes it's hitting the coast, and the wave just bounces and resonates in the coastal offshore environment. And for several hours then you have repeated surges of tsunami along the coast that can be very devastating. Now those deep water buoys have recorded the passage of the tsunami, and they give us a time history, just like a seismogram or a GPS recording of, in this case, the height of the water above that station as a function of time. That's shown by the black curves. And the red curves are predictions from the seismic model that we produced in a couple of hours. So we were able to anticipate the size of the tsunami signal. It was not fast enough to give improved warning at that time. We can automate this now. We could probably do this within 15 to 20 minutes. It's still not fast enough to give accurate warning. So what you have to use is the signals recorded out by the buoys offshore to tell you exactly how big the tsunami is going to be. The Japanese have put another $1 billion in after the Tohoku earthquake to instrument the offshore environment, so they'll see how big the waves are that are coming at them in real time in the future. And that will allow them to try to evacuate people. You can't stop this from happening. You can't build tsunami walls big enough. You would have needed 15 to 20 meter tsunami walls along the entire coastline of Honshu. And in some places, it's going to run up 40 meters. So you can't really stop the wave from coming. You either don't build near the coast or you have rapid evacuation plans. The Japanese only lost around 20,000 people because they did give warning and did evacuate quickly. Probably would have been a much greater loss of life without that. The last example then is the Chile earthquake I want to talk about very briefly. Happened in 2010. It's going to rupture a fault that's about 500 kilometers long along the coast of Chile. In this case, it's a compressional underthrusting earthquake. The Nazca plate is coming in, is going down under South America as South America moves toward the east. This region also had a lot of GPS before. We knew that there was an area here that had not ruptured since the Darwin's travel on the Beagle, ruptured in 1835. A lot of instruments have been put in. These are GPS instruments. And now you can see the vectors are pointing to the right before the earthquake. It's because the fault is locked. The subducting plate's coming in from the left. It's dragging the coastline to the right. You can see that deformation building up, so you can see it flexing before it breaks. You could identify where there is strong strain accumulation. This is the area that had ruptured in 1835. And there's other patches along here that are building up strain for future earthquakes. Now for this earthquake, the reason I mention it is that we have good recordings of high-rate GPS from these stations that were very close into the earthquake rupture, which is in this box. We have tsunami recordings at these stations, NOAA buoys offshore. We have satellite looks at the land deformation before and after, and this tells you the change in position. This is from INSAR interferometry. We had 2 different passages. We have seismic waves. So we can put all these together and invert them in a joint inversion. And the reason we do that scientifically is because each type of data gives us different information about the source. And what we want to know from a source is we want to have good time resolution of when it ruptures, spatial resolution of how that rupture is spread over the fault, what areas slip more, what areas slip less, at what time, and we want to know how much it slips. Those are the things that we want to know to characterize quickly to evaluate the overall impact of the earthquake. Seismic waves give us good time resolution. INSAR gives us very good space resolution on land, but no time information because the satellites go by every few days. It doesn't give you precise timing. High-rate GPS has both seismic data and offset data that give good space and some time resolution. So we use the different types of data together to try and get the best overall model. I'll illustrate how that works. Up here is a model where we're going to put in a silly-looking slip distribution of large slip, no slip, large slip, no slip, large slip. And we're going to make a synthetic calculation for a rupture that expands on that fault with this arbitrarily complex geometry of slip. When we calculate the GPS signals, the seismic signals, the tsunami signals that model would produce, and we invert them to see how well we can recover what we put in. If you invert from the GPS stations were all right here. They do a good job of recovering locally the structure, but they do poorly out here. It doesn't look like the input model. Each data set is going to have limitations from where the stations are and the intrinsic nature of the data. The seismic model does pretty good at recovering the deeper part of the fault, but it doesn't do well offshore for the very shallow part. It doesn't make this reconstruct this checkerboard pattern. The INSAR data, which is just for reflection off land, does very well for the on-land part of the fault, but it does very poorly offshore because it has no information. You can't see the seafloor deformation. In complementary fashion, the tsunami does very well offshore at recovering the input model, but it does very poorly onshore. So what we're doing in the current research is put all the different data together, exploit their complementary sensitivity, and see how well you can do. And this is the joint inversion. And now you can see this looks a lot like the input model. So by being holistic and using seismic and GPS and tsunami data all together, we can get the best overall characterization of the faulting. This is just showing the fit to the actual data. These are the GPS signals with these little static deformations. These are seismic signals. These are tsunami signals. These are residuals of the INSAR fitting. It fits the data all very well and gives us a model that looks like this. This region with 20 meters of slip that goes all the way to the trench in the north, 10 meters of slip down here to the south. The earthquake started here, and this is the area of the seismic gap where Darwin thought the earthquake in 1835 had occurred, or where we thought the earthquake occurred. And there was no slip there. So it's one of these, we were right for the wrong reason. We knew this region could have a big earthquake, but the area that we had anticipated there would be a big earthquake didn't slip significantly during the event. Instead, there was very large slip up where the region had failed in 1928. So again, we are surprised, and we don't have the ability to anticipate what will be the slip distribution in the next big earthquake because it's very complicated from event to event. So let me summarize briefly. From analysis of the great earthquakes and using these expanded data sets of seismic and GPS and tsunami signals and developing integrative tools to analyze them all together in a self-consistent fashion, we've been able to characterize a lot of the big earthquakes that have happened. We've seen processes like one giant earthquake affecting the adjacent region of the fault that happened between 2004, 2005, 2007, Sumatra, kind of zipping along the fault, but it can leave a gap. And there is a mentawai gap that is an area unbroken in between a couple of patches that slipped. We had seen this type of behavior before in the 40s and 50s, so it was not terribly surprising. We saw the Solomon Islands, an example where you could rupture right across a break in the underthrusting plates, or two different plates, or a very warm, perturbed part of the plate where we didn't think earthquakes could occur. There are many areas around the Pacific where we have argued that there will not be large earthquakes because there's big volcanic structures being subducted. This was a counterexample. It shows that, in fact, those areas can have big earthquakes that rupture right across a triple junction in that case. We've seen other events that could rupture down dip in a large earthquake, but then have a large earthquake at shallower depth. I didn't talk about this, but this could be a very tsunami-genic type earthquake. Saw the 2011 Tohoku earthquake rupture the entire width of the plate boundary contact with very large slip at shallow depth, where we would not have been able to tell that there was large strain accumulation from the onshore GPS, and that produced huge tsunami. We've seen thrusting between the plates activate breaking of the plate, the Kuril Island sequence in 2006, thrust and then breaking, and the reverse, where you had breaking of the plate induced thrusting. So all possibilities appear to be possible. And we wouldn't even have speculated about several of these before these earthquakes. We had no basis for understanding because we had not been able to quantify prior great earthquakes in detail. Well, this is a cartoon. We think that there's a lot of variation on every fault in terms of the frictional strength. Attempts to display that. These bright red areas are areas that are very strong, that make strong patches that fail in large slip areas on the fault, like we saw for Tohoku or for Sumatra earthquake, 10 to 20 meters of slip or even larger. In some cases, it can drive slip up to very shallow depths and produce very tsunami-genic failure near the shallowest part of the fault. You produce very large ocean floor displacement that makes big sea waves. Or down dip, as you go, there can be patchiness, smaller regions that slip and produce strong shaking right under the coastline. And this is a real concern for Cascadia, is that even if there is a large slip event far offshore, it will be tsunami-genic, but the down dip part of the fault can have strong patches that fail right under the coastline. And those in the Tohoku event were the regions that were responsible for the 2G ground accelerations that were experienced, where the offshore slip that produced the tsunami did not produce strong shaking onshore. Okay, so in summary, there's been a lot of big earthquakes. We have great data for the first time to capture these earthquakes. Part of that's been developed by IRIS and the GSN. Part of it's been the emergence of the technologies of GPS and the sophistication of rapid analysis from increasing constellations of sensors. The deployment of more ocean bottom pressure sensors to give us deep water tsunami recordings. When we collect all those data in real time and process them rapidly using advanced techniques that exist in many groups now, we're able to get very good characterizations of the faulting geometry and slip distribution and tsunami excitation. And for future events, we should be doing better and better at identifying where there has been damaging shaking, where there has been tsunami excitation. So I think that we're making good progress in this field, and we just need to wait for the next big earthquake to try it all out. Thank you very much.